This is an overhead crane, common in industrial environments. Overhead cranes are capable of lifting loads anywhere from a few hundred kilos to a few hundred tons. To move such a load from point A to point B, and to do that with pinpoint accuracy, a number of powerful, reliable, and safe electric motors are needed. How to build an electric motor that is capable of doing all that? Electric motor manufacturer KONESKO makes a wide variety of electric motors, some no bigger than a coffee mug and weigh almost nothing. Others comparable to cars and weigh over 2.5 tons. Even though electric motors differ in size and looks, the basic working principles remain the same. So do the components they are made of. These are a shaft, a rotor, a stator, bearings, a frame, end shields, a brake, a fan for cooling the motor, and a conduit box for connecting the motor with a power source. The assembly of an electric motor is quick and almost effortless in the hands of a skilled engineer. But this is just one and the very last step of the manufacturing process. Making an electric motor from scratch, however, is a whole another ballgame. It requires unparalleled precision, a lot of man-hours, and it all starts here. In a large warehouse, where all the raw materials are stored. Here, depending on the type of motor being built, a steel rod is selected, placed on the cutting line, and sawn to the correct size. This rod goes then through a number of computer numerical control machines, aka CNC machines. And after extensive turning and loads of emulsion, this is what emerges. A shaft for our electric motor. At the same time, on the other side of the factory, blanks are being stamped from the sheet metal. These blanks are then further processed and divided into stator and rotor laminations. If stator laminations are stacked and welded together, then rotor laminations are stacked and cast together. For that, a molder fills the grooves of the stacked rotor laminations with molten aluminum. This procedure is only seemingly simple. In reality, it requires flawless execution and must be carried out under very specific conditions. Pour it slightly unevenly, and air bubbles will fill the grooves. Cool it too fast, and the metal shrinks, resulting in vacuum bubbles. Do it in higher than required humidity, and the composition will be completely ruined, as excess water in the air will end up in molten aluminum, where in turn, it breaks down to oxygen and hydrogen, forming unwanted oxygen slag and hydrogen bubbles. After proper cooling, the previously made shaft is pressed inside the rotor. Next, the exterior of the rotor is turned to the correct size, using a metal lathe. This is another intricate step that requires pinpoint accuracy, as the rotor must not only fit inside the stator, but also needs to rotate there at high speeds. On top of that, the gap between the two, a rotating rotor and a stationary stator, must remain precisely 0.3 millimeters at all times. That is thinner than a standard business card. At the end of this phase, the rotor is balanced and the ball bearings are mounted to it. Meanwhile, a recently welded stator goes through a process called winding. That is probably the most labor-intensive step of the whole production. First, the slots of the stator are individually insulated. For that, a special dielectric paper made from Nomex and Mylar is used. Next, enamel copper wire coils are inserted in the insulated slots. Finally, all the necessary cables are attached, and the stator is laced. That is done to secure the field coil ends to avoid any involuntary movement and vibration when the motor is operating. Depending on the size of the stator, the whole winding process takes anywhere from 2 hours to 2 weeks to complete. Wound stators are all thoroughly tested, and only ones that pass this rigorous exam will be cleared for impregnation. Vacuum pressure impregnation is a process by which a fully wound stator is completely submerged in resin. To carry this out, stators are bundled and placed in a large pressure tank, which is then filled with resin. Through a combination of pressure cycles, the resin is assimilated through the stator's windings and insulation system. Impregnated stators are left to drip dry and thereafter thermally processed. Applied heat will turn resin-covered windings into a solid monolithic structure. This results in greater durability, increased safety, and a longer lifespan, as impregnated windings have better thermal inductivity and dielectric strength. Properly impregnated stators also require a lot less maintenance. The housing of an electric motor is usually made of cast iron or aluminum, and it is attached to the stator using nothing but heat. The aluminum frame is kept in an oven at 200 degrees Celsius for 20 to 30 minutes. That makes the metal expand and allows the housing to be slid on the stator. As it cools, the housing shrinks and grips the stator. This grip is so firm that no additional fasteners are needed. After impregnated stator is housed, there is nothing left to do but put the motor together. For that, an engineer gathers all the previously made parts to the assembly station and assembles the motor, carefully following the drawings every step of the way. KONESKO manufactures around 90,000 electric motors in a year, and every one of them is individually tested. During this final inspection, the finished motor is carefully checked and put through several load and stress tests. All the results are archived, and only motors that perform as intended will leave the factory and will be delivered to the client. Assembled motors with aluminum housing will go straight to final testing, while motors with cast iron housing receive a paint job before that. Here, after treating the motor with white primer, painters give it a specific color, or if a client desires, a completely custom look. If a greater quantity of any given motor is needed, then manufacturing is moved to a fully automated production line, and the work is handed over to the machines. In that case, almost every step of the production is handled by intelligent robots.